we're now starting a new section. We're going to be seeing how to manage memory. How do programs allocate memory as they run so they can use it for their data structures? Okay? So this section is a little long. It has quite a few parts to it. Okay, we're going to start with a quick intro right now, and then we're going to see how dynamic memory allocation works. And the reason we need dynamic memory allocation is because the size and number of data structures may be only known at runtime dynamically. Okay? And then we're going to see how we implement that dynamic memory allocation in a number of ways. We're going to look at something called garbage collection, which automates a lot of the memory management process from the programmer's point of view. And then we're going to see how memory-related bugs really can make your life hard, and what are some of the common memory-related bugs in C that happen, and so you can avoid them in your code. Okay? So what is dynamic memory allocation? The first thing to realize is that it's often impossible for a program to know how much memory it's going to need until it's actually running. Let me give you an example. Suppose that you write a piece of code that takes whatever the user is typing on the keyboard and stores it in memory. Well, until the program runs, it doesn't know how much the user is going to type, so it doesn't know how much memory it's going to need. Okay, so and therefore it's not going to allocate it on the stack. So we're going to allocate this in a region of the memory layout of the program called the heap. Okay, so the heap is where dynamically allocated memory goes. It's a region of the heap that where when programs allocate memory dynamically, that's where it's allocated from. Okay, so the programmers use dynamic memory allocators such that they can acquire memory at runtime. They can acquire pieces of its address space at runtime to store data. Okay, again, this is for data structures that are only known at runtime. For anything that's known statically, you can allocate this in a different part of memory. We're talking about the heap is everything that's allocated explicitly. Okay, and we're going to be using something called Malloc as our dynamic memory allocator, which I'm sure you've seen. So the dynamic memory allocators, they manage this part of the address space, as I said, called a heap. Okay, there's a region here of your address space. That's where all of your regions of memory allocated with Malloc go. So let me tell a little bit more about the allocators. Okay, so as I said, the allocators maintain a heap. Right, the heap as a collection of blocks. Okay, they can be of different sizes, and these blocks can either be free or allocated. Okay, so and these blocks reside in the heap, and the heap region itself might have to grow, because if the program allocates a lot of memory, the region set aside, the region of the address space set aside to the heap might not be large enough, so the process has to request to the operating system more chunks of the address of the virtual address space to have the heap there. Okay, so since application objects are typically smaller than pages, the allocator manages blocks within pages. Okay, so but that's not a restriction. Applications could have objects much bigger than pages, but typically they're not. So the allocator, so this is not done by the operating system. This allocator runs in user space and manages the actual smaller blocks that form the heap. Okay? So there's two basic types of allocators, called the explicit allocator, where applications both allocates blocks and frees the blocks. That's what Malloc and free does in C. It's explicit because the program explicitly requests and explicitly frees up them. There's also something called implicit allocator. So using this allocator, the application requests memory, allocates memory, but does not free it because that's done automatically. Okay, and this is what garbage collection is in, say, Java, ML, and Lisp. So we're going to be looking at the Malloc package. This is part of the standard C library, and here's what Malloc does. Malloc receives a size as a parameter. That's the size of the block that's going to be allocated. And it returns a pointer that doesn't have a type because we don't know what kind of data is going to be there. Okay? So if it's successful, it returns a pointer to the new memory block that has at least size bytes. Okay? And if the size is equal to 0, it returns no. Okay? Because then why are you allocating if the size is 0, right? No. So, and if Malloc cannot find enough free memory to allocate the requested block, it returns null and sets an error number. So you know why that happened. And now free doesn't return anything, but it takes as a parameter a pointer p that is a pointer to the beginning of a block. Okay, so and p must come from a previous call to malloc or realloc, but a realloc just resizes the size of a block. Okay, and what free does, it returns this block pointed by p back to the available pool, so it can be used in the future. So let me give you an example. By the way, the other functions are also calloc, that is essentially another version of malloc that sets the allocated block to 0. Realloc just resizes the block. And sbreak is used internally by the allocator to grow or shrink the size of the heap. That's a system call. Okay? So now I'm going to give you an example. Suppose I have my function called foo here. It has two parameters, int n and int m. And what we're doing here, and there's a pointer p here. When we call malloc, what malloc is going to do is going to get n and multiply by the size of int. So it's going to allocate an array of ints. Okay, so this is an int, and it's going to have n elements. So the size of this array is n multiplied by the size of ints, and that's what we pass to malloc. That's the number of bytes we want to allocate. And since we're going to be storing ints, we cast the pointer returned by malloc to a pointer to an integer, to an int star. Okay? So if p is null, that means there was a problem with malloc and the process exits. Right? Malloc might not have found enough free memory. But if it's not null, that means that right here we have a valid pointer stored in p. So now we can execute a loop that just populates that this array here with 0, 1, and so on. Okay. So, but now let's say that this wasn't enough. So we could call realloc, which takes p, the original block, the pointer to the original block as a parameter, and takes a new size. And what it does is it just resizes the block and returns a new pointer, okay, which might not be the same. So now we can go and extend it. We can write more elements. So realloc just extends the array here, and then we can go and start using this again. And now we're going to print a new array and so on. Okay, see you soon.